In the chapters of the course so far, we have collected many examples of varieties, so affine varieties, projective varieties, and last chapter we discussed these Grassmannians. And we also have nice construction techniques, taking the old varieties that we know and constructing new ones, such as gluings and products and so on. And what we do in this chapter is look at some pairs of examples of these varieties, which are almost the same. So, for example, you can take X, the product of Pn and Pm, and Y, just the projective space Pn plus M. So we know these are both projective varieties. They're both of dimension n plus m, and they have even a bit more in common because, well, in this product here, because an is an open subset of Pn and am is an open subset of Pm, we know that the product an cross am, which is just the affine space an plus m, is an open subset of this product here. But this an plus m, this is also one of the standard open charts of the projective space Pn plus m. So this means in this variety X and in this variety Y, there are copies of this affine space an plus m. And of course, these are isomorphic. It's just the same open subvariety. So there's a big chunk of these varieties, this dense open subset, which are isomorphic, but there is another exercise in the script which shows that the full varieties are not isomorphic. So that's a kind of strange combination. And similar, we have that if we have the variety A1 and this variety here, this vanishing set of y squared minus x to the 3, it's called the cuspidal curve, then we have seen that there is this map from A1 to y, which sends t to t squared t to the 3. And we have checked on the coordinate rings that this is not an isomorphism. On the other hand, you can also check on the coordinate rings that if you remove 0 here and the origin here, then this map becomes an isomorphism of these open subvarieties. Because essentially then, if once you remove the point 0, 0, then you can write down the inverse of this map, which sends xy to y divided by x. So again, we have the situation that we have a big, dense open subset in x and in y, which are the same, which are isomorphic, but x and y themselves are not isomorphic. And so this we want to talk about more. So in this chapter, we developed a language to describe this phenomenon of having isomorphic open subsets and show a new construction, which is called the blow-up, which takes a variety and modifies it locally around a closed subset, leaving the complement of this closed subset, an open subset, unchanged. And that's then one of the examples of having dense open subsets which are isomorphic. And the right language for this is the language of rational maps. So for this discussion, we will have x and y be irreducible varieties for simplicity. Then a rational map, which is denoted like this. It's almost like a map, but the arrow is dashed like this, is the data of a morphism from u to y, where u inside x is a non-empty open subset. So in other words, defining a rational map, you don't have to define it on all of x. You only have to define it on some open subset, which is then necessarily dense. And you also define an equivalence relation between rational maps. If you have two of these things from x to y, which have domains of definition u1 and u2, then they are equivalent if inside the intersection of u1 and u2, there exists a non-empty open subset u on which these two maps agree, right? Because f1 and f2, they are defined on u1 and u2, so restricting them to u makes sense. So this is still a locus where they are defined, and then you can compare them on this overlap. We're going to have an example in a second, but then we define the rational maps from x to y as just all of these partially defined maps, so all such morphisms defined on a open subset u of x to y modulo this equivalence relation. And if you want to check for yourself that this is indeed an equivalence relation, then the transitivity part, you will see that you will use that in this irreducible variety X, these open subsets U are always dense. Okay. And so here is a kind of small example. So inside, if here X and Y are both A1, and then inside A1, you have the open subset where you remove the origin. And once you do this, you have a morphism to A1, which sends X to 1 over X, because this is a regular function on here. This gives a nice morphism. And so this is a non-empty open subset. And so this defines just the data as above. This defines a rational map from A1 to A1. And you see, I mean, it's not possible to extend this map over the origin, because there, this function has a pole. It would no longer be a morphism there. And then we can write down a second map, which is defined on A1 minus 0 and 1 to here, but it's just given by the same recipe. So this removing the 1 wasn't really necessary, but we can, of course, do it. Then you get a new open subset U prime. And the claim is that this map and this map are equivalent in the sense above, because, for example, on the overlap U prime, they define the same map. And so somehow removing this point 1 actually didn't change the rational map. So this equivalence class in here, represented by this morphism. Okay. So yeah, that's the kind of idea. We don't really want to consider these two to be different. And that's the reason why we have this equivalence relation. The first remark is that, I mean, in this definition of equivalence, we saw, I mean, F1 and F2, they're defined to be equivalent if they agree on some non-empty open subset, should be non-empty, of this intersection here. But in fact, we claim more is true. We can always just take U to be this intersection. So we were a bit more careful in the definition that we actually had to be. And the claim is that, in fact, F1 and F2 agree on the biggest open set on which they are both defined, namely this intersection here. And this just uses, well, if they agree on a possibly smaller open set U, then, well, this intersection of sets in this irreducible variety X is still an open subset, still dense, so it is still irreducible. And so U inside there is still dense. And on the other hand, we have seen the target, when the target Y is a variety, when it is separated, then the locus where the two maps here agree, a priori they are defined on here. So they give a morphisms from U1 intersected U2 to Y. And then the locus where they agree is closed in their domain of definition. And it contains this dense open set U. And so it must actually be everything. So you can always be sure that two of these maps agree then on their entire domain of definition. And now we have defined some kind of nice notion of morphism, some rational map. And then you would hope maybe we can get one of these categories out of this. So let's say the category has objects, irreducible varieties, and as morphisms, you just take these rational morphisms. So does this work out? Well, there's one problem, and namely in a category, you want to have a composition map. And so let me show you two very nice rational maps from A1 to A1. Namely, the first one is actually a morphism defined everywhere. It just sends all X to 0. It's the constant morphism. And G is the rational map that we have seen before, which sends X to 1 over X. And the problem is, how would you define the composition here? Because F sends everything to 0, but 0 is the one place where G is not defined. So somehow there's no good way to make sense of this composition here. And so this category, exactly as it's formulated here, this doesn't make sense. This wouldn't work. So we need one more idea, And in fact, the next definition that we're going to see exactly brings this idea and also makes precise this notion that we had before, the two varieties almost agree. So we start again with x and y irreducible varieties, and then such a rational map from x to y is called dominant if the image of f, I mean, it's defined on some open subset of x, and so it has some image in y. We want that this image here is dense inside y. And it's a small argument that you can check for yourself that this is actually well defined on this equivalence class. If you have two equivalent morphisms, F1 and F2, then their images or the image of F1 is dense in Y if and only if the image of F2 is dense in Y. Okay, and so if we know this property of being dominant then allows us to do these compositions. Namely, let's assume, so we have a dominant morphism from X to Y, a dominant rational map, I should say. And let's say we have any rational map then from G from Y to Z, going on to some further variety. And let's say this G is defined on the non-empty open subset V inside Y. Then we claim that then we can write down this composition here as a rational map from X to Z. And so why does this work? Well, we can define, so G is defined on V, and so somehow this composition, then we only want to allow places inside the domain of definition of F, which are sent into V. On there, we can really compose these two morphisms. So this map would be defined on the pre-image of V under this map F. And we have that the image of F is dense in Y, and V is a non-empty open subset of Y. And so by basic topology, the image of F must intersect V. And so the pre-image of V is non-empty, it's an open subset of X. And so we do get a well-defined morphism from this open subset to Z. And so we can define this composition. So we're going to remark this in a second, but this will allow us to define a nice category. Okay. So the upshot, what you should remember is that when you have dominant morphisms, dominant rational maps, then you can compose them. And so we call a rational map from X to Y birational if it is dominant and there exists also dominant map G in the other direction, such that the two compositions give you the identities. And these equalities here are really equalities of rational maps. In other words, these compositions, they agree with the identity on some non-empty open subset. And you see, this is exactly the kind of notion of isomorphism. You have an inverse map in this space of rational maps. And then finally, so somehow this is saying when is such a rational map birational, and then X and Y are called birational, so these varieties, if there exists a birational map between them. And this is the kind of notion of isomorphism. And so I should make this precise. So somehow we do get a category, the objects are irreducible varieties, and the morphisms are dominant rational maps. This is the clue. Then we can write down a composition. We also have that the identity is always a dominant rational map. And so we get this category. I just call it here the var k varieties over k with dominant morphisms. And then you can check in this category, these birational maps are exactly the isomorphisms. And being birational is exactly the same as being isomorphic in this category. And we started the lecture with this kind of motivation of identifying two varieties if they contain isomorphic non-empty open subsets. And so what does this have to do with this notion of being birational? Well, this is the thing that the next lemma is going to discuss. So if x and y are irreducible varieties, then they are birational if and only if they contain isomorphic non-empty open subsets. So x contains some open subset u, and y contains some open subset v, and u and v are isomorphic. And so one direction is pretty easy. If you have this assumption here, well, then you see this morphism here is defined on non-empty open subset. So it is a rational map. You can just identify this. It's a rational map defined on U in this direction. And it's also dominant because, well, V is contained in the image and the closure of V is everything. So the image is dense. And on the other hand, well, the inverse is also a rational map, just taking the inverse of this isomorphism from V to U. It's also dominant. And if you do two compositions, then you get either the identity on U or the identity on V. And these are rational maps equivalent to the identity on X and the identity on Y. So somehow, if you have isomorphic open subset, it's clear that you are birational. The other direction is just slightly more tricky. So somehow assume that you have f from x to y birational, which is defined on U, and g from y to x, the inverse birational map defined on v inside y. So this is the situation. You have x and y, and then on the red part U, you have a map f, and on the green part V, you have the map f inverse. And then we just need to find some open subset here isomorphic to some open subset here. And you have to think a bit about which is the best open subset to take. And essentially what you want to do is you start with U here, and then you take the inverse under this composition here. So somehow, yeah, I guess here this is G. So somehow you first take the pre-image of U here, and then the pre-image again on the F. So this here is an open subset of X. This thing here, you do the opposite way, starting with V. This is an open subset of Y, and then you can check just that F sends this open subset to this open subset, and G conversely, and that the two compositions are the identity. So this is how you get these isomorphic open subsets. You just take 2 times pre-image like this. Okay, and as a nice consequence, we have seen in an exercise that we can compute the dimension of first of all an affine variety, but then also of any irreducible variety. We can compute this by computing the dimension of any dense open subvariety. And so if you have two birational irreducible varieties, then they have these isomorphic open subsets. And so the dimension of U and V agree. And so also the dimensions of X and Y agree. So that's a nice thing to remember. Birational irreducible varieties, at least you know the dimension is preserved. So this is the same. And just to conclude with an example of some birational varieties, we just copy from above, and then we see that by this criterion from the lemma, we know that Pn cross Pm is birational to Pn plus M, and similar that A1 is birational to this variety Y here. Okay, and so then we continue the study of these birational maps in the next videos.